friends, this is Kruti Jaipancholi, Assistant Professor in LJ Institute of Engineering and Technology in Department of Electronics and Communication. So, this video is about subject fiber optic communication. So, friends, till now we learn about the light sources, about the LED, laser. So, in this video, we are going to discuss about particularly the distributed feedback DFB laser. So, in the last video, we have also studied about the Fabry-Perot resonator. So, in the DFB laser, the lacing action that is obtained by the periodic variations of the refractive index along the longitudinal dimensions of the diode. So this is mainly the principle behind the DFB. So periodic variations of the refractive index along the longitudinal dimensions of the diode. So here you can see the diagram of the DFB laser. Now this DFB laser, okay, so now here the various confinement layers are there, okay. From the in between we are taking the output, optical output, and here you can see the gratings of the variations of the refractive index. So this is the diagram of the DFB laser. Now the electromagnetic wave which is propagating in the longitudinal direction, which can be expressed as E z comma t is equal to I of z e raised to minus I in bracket the omega t minus beta and the z, where I of z is a optical field intensity, omega it's a optical radiant frequency, beta it's a propagation constant. So this way how the electromagnetic wave traveling onto the z-axis with respect to time that we have seen. So the fundamental expression for the lacing in the Fabry-Perot cavity, that is the Iz is equal to I0 E reflection, okay, gamma G H V minus alpha H of V, okay, H comma V into Z, where this is the gamma, that is the optical field confinement factor, or it is the fraction of the optical power in an active layer. Alpha bar, or the alpha you can write, it is the effective absorption coefficient of a material. G is the gain coefficient, H and V, that is the photon energy, E is equal to HV, and Z, that is the distance traveled along the lacing cavity. Now the condition of the lacing threshold, that is given as for the amplitude I of 2L is equal to I0, for the phase e raised to minus j 2 beta L is equal to 1, and optical gain at the threshold is equal to the total loss in the cavity. So that is why the gamma GTH, that is the threshold gain, is equal to alpha into T, and now the lacing expression that can be reduced to this, the gamma GTH is equal to the AT is equal to alpha plus 1 upon 12 ln into 1 upon R1 plus R1 into R2. Similarly, the gamma TH is equal to the alpha T is equal to alpha plus alpha N. So this is the lacing conditions, where A, E and D, that is the mirror loss in the lacing cavity, and an important condition for the lacing to occur is that the gain G, that is to be greater equal than the GTH, that is known as the threshold gain. So now we'll solve the example related to the previous equations. So friends, the example title is find the optical gain at the threshold of a laser diode having the following parameter value. R1 is equal to R2 is equal to 0.32. Alpha is equal to 10 centimeter raised to minus 1 and L is equal to 500 micrometer. So now optical gain equation. Now these all are the important equations that we need to remember for any of the parameter calculation related to the laser. So the gamma GTH is equal to alpha plus 1 upon 12 ln into 1 upon R1 R2. Put all the values given above, that is gamma GTH is equal to 10 plus 1 upon 2 into 500 into 10 raised to minus 4 ln 1 upon 0.32 into 0.32. So our answer is 33.7 centimeter raised to minus 1. Okay, or the centimeter inverse. So this is about the example related to it. Now the power current characteristics. Now here in the diagram you can see the power current characteristics. On the x-axis there is a current value in the milliampere is given, and onto the y-axis there is a optical power in the millivolt that is given. So now here in this diagram you can see that okay, after the threshold, okay, the value whenever the small optical powers is there, the spontaneous transmission and the stimulated emission that is there. So the optical output power versus the forward input current characteristics for a typical laser diode, that is plotted in the diagram. So below the threshold, only the spontaneous emission that is emitted, and hence there is a small increase in the optical power with the drive current. Now at the threshold, when the lacing conditions that satisfied, the optical power increases sharply after the lacing threshold because of the stimulated emission. So the lacing threshold obtained gain, optical gain GTH, that is related by the threshold current density JTH. So GTH and the JTH, they are related for the stimulated emission by the expression. So that expression is GTS is equal to beta JTH. So where beta is the constant for the device structure. So now the next is the external quantum efficiency. We have also seen the internal quantum efficiency. But now what is the external quantum efficiency? So this is defined as the number of the photons emitted per electron hole pair recombination above the threshold point, which is referred to as a external quantum efficiency. And this external quantum efficiency eta ext, which is given by the eta ext is equal to eta I in bracket GTH minus alpha upon GTH. So this is the equation for the external quantum efficiency, where the eta I value, that is the internal quantum efficiency, and which values is between the 0.6 to 0.7. GTH, that is the threshold gain, alpha, that is the absorption coefficient, and the typical value for the eta ext for a standard semiconductor laser, that is ranging between 15 to 20%. Now the next is the resonance frequency. At which frequency the resonance start or the device resonant, which refer to as the resonant frequency. So at the threshold, the 2 beta L is equal to 2 pi m, where beta is equal to 2 pi m upon the lambda. So m is the integer, small m is equal to 2L into n upon lambda. Since C is equal to V into lambda. So lambda is equal to C upon V. Now put the value of the lambda in the equation, and small m is equal to twice L into N into V into C. So the gain in the laser is a function of the frequency, and for a Gaussian output, the gain and the frequency are related by the expression G lambda is equal to G0 e raised to lambda minus lambda 0 upon the Z0 square. So this is the equation for A, where the G0 is a maximum gain, lambda 0 that is the center wavelength in the spectrum, and the alpha that is the spectral width of the gain. So the delta V is equal to C upon 2ln, and delta lambda that is equal to lambda square upon 2ln. So these two equations are also important to solve the examples related to the resonant frequency for the laser. So this is the equations related to it. Now the next is optical characteristics of the LED and the laser. Now here in the diagram, the characteristics of an LED with the comparison of the laser is given. Whenever the value of the current, the current at the threshold, what happened? That after the threshold, it acts as a laser, and when the current that is less than the threshold value, okay, it can be the operation that is not perfectly as the LED, we can see. So optical power and the current versus the diagram we can see over here. So the output of the laser diode that depends on the drive current passing through it, and at the low drive current, when the low current is there, the laser operates as an inefficient LED. But when the driving current that crosses the threshold value, lacing action that begins. So this graph that shows the comparison between the optical power of a LED operation due to the spontaneous emission and the laser operation that is due to the stimulated emission. So now the spectral and the spatial distribution of the LED and the laser. Now the low current laser diode that acts like the normal LED above the threshold current stimulated emission, that is the narrowing of the light ray to a few spectral lines instead of the broad spectral distribution that exists. So now this enables the laser to easily couple to single mode fiber and reduces the amount of the uncoupled light. That is the spatial radiation distribution. So the diagram for this spectral and the spatial distribution difference between the two diodes that we can see over here. So in the A diagram, okay, that is the spectral distribution of the laser diode, and the second one that is the spatial distribution of the diode. Okay, so now as we can see that how the light rays that can be scattered in case of the LED, and how we can get the sharp beam in case of the laser diode. So that is due to the spontaneous and the stimulated emission. The next point we are going to discuss, that is regarding the advantage and the disadvantage of the laser diode. What are the advantages of the laser diode? As we know, while we see the laser and the LED, the advantages that comes to us directly. So first of all, the simple economic design. That's a good advantage of the laser diode. High optical power. The production of the light can be precisely controlled, and it can be used at the high temperature, provides the better modulation capability. Other advantages of the laser diode are the high coupling efficiency, low spectral width, that is around the 3.5 nanometer, ability to transmit optical output power between the 5 and 10 milliwatt, and ability to maintain the intrinsic layer characteristics over long periods. So these all are the advantages of the laser diode. Now the disadvantage of the laser diodes are, at the end of the fiber, a speckle pattern appears as a two coherent light beams that add or subtract their electric field depending upon their relative phases. So that can be the disadvantage of using the laser diode. And it is also extremely sensitive to overload current, and at the high transmission rate, when the laser is required to operate continuously, the use of the large drive current produces unfavorable thermal characteristics. So that is again the disadvantage of using this. Now the next is the comparison of the laser and the LED. So there are the various parameters for comparing the performance of the LED and the laser diode. So very first parameter of comparing these two, that is the principle of operation. Now the LED that works on the principle of the spontaneous emission, and the laser diode that works on the principle of the stimulated emission. The output beam of the LED, that is the non-coherent, and in case of the laser it is coherent. The spectral width of the LED, that is the broad spectrum of 20 nanometer to 100 nanometer, and for the laser diode the beam that is the much narrower, and it is about the 1 to 5 nanometer. About the data rate, the data rate of transmission using the LED, that is lower, and using the laser it is the very high. The transmission distance of using the LED, that is the smaller, and in case of the laser it is a greater. The temperature sensitivity about the LED, it is less sensitive to the temperature, and the more temperature sensitive, that is the laser diode. The coupling efficiency in case of the LED it is very low, and in case of the laser it is the high. Compatible fibers. Multi-mode step index, multi-mode graded index fiber that are compatible using the LED. In case of the laser diode, the single mode step index and multi-mode graded index fiber, they are more compatible. The complexity of the circuit, that is by using the LED it's a simple, and using the laser it is a complex. The lifetime of the LED, that is the 10 raised to 5 hours, and using the laser diode it is the 10 raised to 4 hours. About the cost, the LED, using the LED, the cost that is laser, everybody knows, and the laser diode, the cost that is the high. Output power, that is linearly proportional to the drive current in case of the LED, and proportional to the current above the threshold in case of the laser diode. How much the current required to drive the LED as well as the laser? So the drive current, that is a 50 to 100 milliampere peak for the LED, and the threshold current to 5 to 40 milliampere, that is required for the laser. The wavelength available. The wavelength, it is the 0.66 to 1.65 micrometer in case of the LED, and 0.78 to 1.65 micrometer in case of of the laser diode. The last but not least, that is regarding the applications of the LED and the laser. The application of the LED, that is a moderate distance, low and the low data rate, and the long distance, high data rate. So these all are the applications or the comparison between the laser diode and the LED. Now, the important formulas for the LED and the laser. Now, important formulas are: the wavelength lambda is equal to 1.24 upon Eg. Then the time, recombination time, it is 1 upon tau is equal to 1 upon tau r plus 1 upon tau n r. Internal quantum efficiency eta int is equal to tau upon tau r, and p int is equal to eta int into h Planck constant c into I upon q into lambda. So this is the equations required to solve the example related to the LED. Now the equations required or the formulas for the laser. So laser, that is the gamma GTH is equal to alpha plus 1 upon 12 ln into 1 upon R1 into R2. Delta V is equal to C upon 2 ln, and delta lambda is equal to lambda square upon 2 ln. So this is regarding everything related to the optical sources that are required in the optical fiber communication. So this is regarding it. So thank you very much everyone.